and excited for our next sessions. A little warm-up question. Do you trust AI with your money? I think you do, but you don't know you do. Actually, this next session is going to be exactly about how artificial intelligence and machine learning are helping keeping our money safe. And for that, I want to welcome on stage Ștefan Filipescu, data scientist at ING Romania, who is going to talk about AI versus fraud. Big round of applause, everyone, for Ștefan. Thank you so much.
Hello, good morning. My name is Ștefan Filipescu, and today I have an amazing investment opportunity for you where you can double your money in just several hours. This might seem funny to you, but our customers are dealing with this kind of fraudulent promises every day, and we want them to not have to deal with this problem. I've been part of the fraud team for the last 3 years, contributing for the first 2 years from a data analyst role, and now I switched to a data science position. And I want to tell you some more today about what we are doing in order to keep our customers safe. Today I will briefly tell you what fraud really is, what is its impact towards society, and how we are building our models in order to make sure everyone is safe. Then I will discuss some more about challenging learnings that we had during our previous use cases, and I will end with some more technical engineering challenges that we faced along the way. I've been looking for a long time for a clear description on what fraud really is, and I stumbled upon the one that you see on the screen in an article from the Bureau of Justice from the United States. It says that fraud is the intentional misrepresentation of information or identity in order to deceive others, the unlawful use of a credit or debit card or ATM in order to obtain money or other things of value. This perfectly summarizes three of the most common type of fraud: impersonation, identity theft, and financial fraud. Of course, there are a lot of other categories, but there are also subcategories that are highly dependent on the way the fraudsters decide to work. And those are usually referred to as modi operandi. For example, if we are looking at identity fraud, our credentials can be stolen either by making use of an existing data breach, or by phishing, or by physical theft. So this is highly dependent on how the fraudsters want to trick people. My intro was not randomly chosen. Probably you recognize a modus operandi that is already very common in Romania, the investment scam, where people are tricked into investing their money in some fake investment opportunities that always sound too good to be true. The impact of fraud is very broad. It's not affecting only the victims, but the whole economy and the trust in the financial systems. And the European countries already highlighted many times that the problem is not only for individuals, but also for private companies and for a lot of public institutions. And that's why we now have, in the European Union, a lot of frameworks that are protecting our customers and that are constantly updated and kept in line with what fraudsters are usually doing. You have to keep in mind at all times that fraud is extremely immoral. And we've seen many times fraudsters making use of crisis or emergency situations in order to gain financial advantages. And we've seen this happening not very far from our border. We've been seeing this happening even since the war in Ukraine. We've also seen this during the more recent earthquake in Turkey. And yeah, this is happening in every emergency situation that is taking place. And what seemed even more shocking than this to me is that I found in a report from the European Commission that 31% of adult victims in the European Union are experiencing emotional or physical harm because they were involved in such situations. And people are not used to talk about this. In the same report, it was mentioned that only 21% of people that are involved in scams are actually reporting this to the bank or to other public institutions that they should. And this is a big problem because neither banks nor public institutions can address a problem that they are not fully aware of. Let's take a closer look to what we are doing in order to prevent this from happening. It's clear, I think, already that fraud is a very big problem, and the fraud attempts are getting more and more sophisticated every day. In order to do that, we are building machine learning approaches that are able to pick up early signs of fraud and to understand the general fraud context. We are using a wide range of data that is able to fully describe both the transactions but also the general behavior of the fraudster. So we can understand the entire context around fraud. We have two different approaches when it comes to building models. We either scale up models that are already existing in a certain country to other countries where ING is present in order to make sure that we are covering as many areas as possible. But in the same time, whenever we spot another developed direction, we are building new models that can cover the topics that are not covered already. Our models are not standalone, but they are part of a much greater prevention system. And because of that, regardless of the options that we are using for building our models, we have to adapt our solutions to the existing architecture and to the needs of the fraud investigators. Let me show you how are we using our fraud models. You see here a very common flow of information inside the prevention system. You see that everything is starting with the customer that is initializing a transaction. All the information about the transaction are then forwarded to an internal payment system that is doing multiple checks. At some point, this system has to decide either if the transaction is legit or if it is part of a fraud attempt. In order to do that, the payment system is using a risk engine. This risk engine is, technically speaking, just a collection of algorithms and rules that are developed by the fraud experts that are able to trigger whenever they spot suspicious activity. We are deploying our model inside this risk engine, and we are sending the predictions to the risk engine just as another variable inside their system. So the fraud experts can further use the predictions that we are doing inside their algorithms. Once the risk engine is reaching to a conclusion about the validity of the transaction, the response is sent back to the payment system that is formulating the final answer that has to get to the client. This final answer has to get to the client as soon as possible. Usually this is happening in just several milliseconds. And that's the main reason that brought us to deploying our models inside the risk engine. We have to have a very high speed, and therefore we don't have enough time to bring our predictions from outside because it would induce some more latency than we can cover. I mentioned to you that we are scaling up models. In order to do that, we had to design our entire code base to accommodate the reusal of code, both inside one project, but also across different projects. You see now on the slide the most common type of model development pipeline that we are using. You see that there are blocks that are colored in orange, and those are stages that have to be built unique for each use case, and then are purple blocks that are partially or fully reused across different projects that we are working on. Let's take a closer look to each step in the pipeline and discuss more about them. We first have data preparation. This includes data understanding, data processing, and everything that has to do with raw data. Even if the general context of our models is extremely similar, we still have a lot of differences in terms of data quality, in terms of data format, or if you are looking at labels and storage, there are also different solutions that are being used. So for example, in terms of labeling, there are countries that are considering as fraud all the fraudulent attempts, regardless of the success status. But there are also some countries that are considering as fraud only those transactions that have a clear negative impact towards the bank or towards the customers. So this is quite different, and approaches are different. And in the same time, if we are looking at the storage, there are entities that prefer to store their entire data sets in just one table, while there are other cases where people are splitting their data across different very small tables that have to be joined by us during processing. Another key part is when we are doing data ingestion. We realized that this process is extremely time-consuming, and it's extremely costly in terms of money. So we are always scheduling it way in advance to make sure that there are no possible delays in the delivery of the model. Based on the past experience, we realized that technical model documentation is also playing a key role in standardizing the process. Maybe sometimes it's helping even more than the code, because if you have written down all the decisions that you take during model development or during data processing, it's much easier for you to come back and look at the current version of your code and understand why did you get to this current version and why you did take some decisions at some point. We have then history calculation, and this history calculation is helping us understand the behavior of the customers. What we are doing is to collect past records from their transactional history with respect to a certain variable and analyze what is their usual behavior with respect to that. We are having this stage fully duplicated around our use cases, and we've also learned that the settings in terms of how long in the history should we look in order to make sure that we are covering all the possible problems, and how many records are usually in this kind of histories. This is common across multiple use cases. If we are looking at feature design, we realized even since the beginning that the features that we are building can be reused. So that's super clear even since we started building this model. However, we realized that the power of our models and the performance of our models is greatly improved if we are introducing some elements that are super country specific, because there are differences in terms of how fraudsters are working between two different cultural areas. So we have to adapt the model and the features to those needs. Therefore, we are splitting this stage in two main parts. One for duplicating our previous work, and another one where we are building features that are customized for the use case that we are working on. One aspect that I want to highlight here is that the business knowledge is playing a key role here. We've seen that the features that have the most impact in terms of importance in the final predictions are those features that were built in collaboration with fraud experts or fully by the fraud experts. So this is helping us to make our models better and to have a positive impact inside their day-to-day business. We then have three different stages that are combined. We have feature calculation, feature selection, and model tuning. We are here trying to obtain the best configuration for our models by iteratively looping over these three stages. Around 90% of them are duplicating from use case to use case. And we've also learned that in general, the model types that we see that are working on similar data is exactly the same, but the hyperparameters that are needed in each case are sometimes completely different. Once we are done with the model configuration and we are getting to this optimal setup, we consider the model development to be over, and we are testing our model on some data that we did not choose for training. And whenever it is possible, we are even using real-time environments where we can understand better how the model is behaving with respect to certain criteria that we are choosing. After testing the model, we are sending our models to production, to the engineers that can put them live. And we've seen that this is quite problematic sometimes, because putting a model inside the risk engine is not a very common task. So the engineers sometimes have to spend some more time understanding what's the best configuration that they should use, and to understand how can they make everything work perfectly. We are seeing these delays most of the time either because there are different software versions that we are dealing with, or because the model is not perfectly translated from one format to another. And I've been mentioning, I think the third time now, about this model format that we are using, and I did not get into detail. We are using the PMML format, the Predictive Model Markup Language. This is an XML format where we have some clearly defined components. We have some steps for pre-processing the data, a data dictionary. We also have tools that can help us with outlier handling or inputting the missing values. We have the model itself, and at the end we can have a step for post-processing the predictions. Let's now slowly go towards the engineering challenges that we faced along the way. The first one that I will be mentioning is targeting feature creation. When we started doing this, we were calculating our features using Python due to convenience on our local machines. We were training the model, we were putting the model into production, and when it was going to production, we were using some features that were calculated with another software inside the risk engine. So we were seeing quite some differences between the features, even if the logic of the features was exactly the same. We started investigating it. It was very hard because there were delays between us calculating our data on our local machines and the risk engine calculating them on the server side and then giving us the feature values and the predictions. But we realized in the end that it was only about some cumulative arithmetical errors that were piling up and that were causing us these big problems. We decided to change our approach towards this because we were seeing that the predictions were quite significantly differencing. So we are now using the risk engine for creating our features, both during training but also on the production side. Then we have, again, history creation. I mentioned to you already what is happening behind. We are collecting records from the history of our customers to understand their behavior better. You can see here on the right side of the screen how our data is usually looking like. We have here 3 different transactions. Each of them is colored differently. And each transaction is composed of multiple events. We have, for each transaction, multiple initialization events and one and only one authorization event. Whenever we are doing this collection, we are collecting only the authorized records to make sure that the payment is already went through the entire payment system and the money actually left the accounts of the customers. We try to mimic perfectly the history creation from the server side. So we started implementing it, and at some point we realized that it's taking way too much time, and it's not very feasible to do this during our model development. So we started optimizing the entire process. But we said in the beginning, we don't want to touch the code of the query, but we want to focus more on things that are easy to access in terms of engineering. So we started optimizing our components that are pure Spark. So we created our own executors that were extremely suited for the task in question. We also started removing the load from the executors. We removed a lot of columns, and we tried to get to make the task as easy as possible. And we also try to work with the structure of the data. We try to repartition our entire data so it can perfectly fit the task. But we realized that, again, it is impossible to do only these types of optimization. It was still taking way too long, so we started changing the code. We did changes on the code one step at a time, and after each step that we were doing, we had to fully validate the entire output to make sure that we are not interfering in any way with the logic of the process. In the end, we were successful. We were able to optimize the task from several days to just several hours for a use case that involved more than 10 million clients and run around 1 billion transactions. I mentioned to you already that we had in the beginning problems with deployment. And this was happening because engineers did not really have experience in deploying models inside the risk engine. We were doing the deployment just at the end of model development usually. So we were adding a lot of time between the moment our model was ready and the moment the model was actually predicting in the live environment, in the production environment. So we decided to take some action towards this, and we designed quite agile way of working where we are now sending intermediary versions of the model to production, or at least to the testing environment, to make sure that the engineers are accustomed and have everything set in place until for the moment we want to actually have the full version in production. We implemented this quite some times already, and we realized that only 3 such cycles are enough to make sure that there are no delays in when we are sending our final model to production. I mentioned to you in the beginning that I've been 3 years already with this team. However, the team is here for a much longer time than I was. And therefore, it reached a level of maturity that involves a wide range of model and a high number of models that we have already in production. So we decided that we need a platform that can help us some more to keep track of what's happening with each model and how each one of them is doing. Therefore, we decided to create 3 different data flows that can help us get this information. We designed one that is run only at the moment of deploying the model into production, that is calculating the performance on the holdout data and can help us use a reference in our calculations and in our observations of the model in the production server. Then we have a second data flow that is scheduled using Airflow and is based on the live data. We are calculating data weekly, we are calculating the performance weekly or monthly, and we are sending all this information to the final table. And we have also a fallback method that is triggered by hand whenever we see that certain data were not calculated because of whatever problems are happening, missing data or other problems on our side. We are triggering manually this thing to make sure that we are filling up the historical values. We are bringing all this data together, and we are aggregating everything and exporting them to the dashboard that we created. The last challenge that I want to mention is it's targeting some PySpark optimization. These are not really problems, but are more challenges as they rarely appear, or they are just optimizations that can be also done manually on our side, but we want to make sure that the execution is as good as possible. The first thing that I will be mentioning to you is a case that we've only seen once and has to do with the way we are calculating our histories. So we are, at some point, limiting the number of records that we are putting inside these histories. And we had a case where we had multiple transactions with exactly the same timestamp, and we've seen that when we are calculating for two different cases, we were having different feature results. And this was happening because we were limiting the number of records exactly between those two records with exactly the same timestamp. And we did not have a safe way to make sure that every time the same record stays in the data set. So we were left with two different data sets that had one record difference. And therefore, our entire feature set was off by quite some digits. And therefore, we switched to some code that was, in the end, showing us the same results, and to a more safer way of sorting these records by timestamp. Then there was something again about feature creation, where we were seeing that the time, even if our new approach is quite balanced, we were still experiencing a lot of time delays, and we decided to further optimize it by removing excessive joins, excessive Windows functions that we're dealing with. We even optimized the execution plan and standardized the code to make sure that everything is much faster. What we also did, but this is quite experimental now, we are not using it in production, we try to remove any intermediary table so that we are going with our pipeline from raw data to the final predictions without saving anything in between. And indeed, with this experimental approach, we were able to speed up the entire process up to 10 times, and we reduce the amount of data that we are storing around 100 times, because we are getting rid of everything that we saved, so therefore we are left with the initial raw data and the final predictions. Another problem that we faced is that, as I mentioned before, our data is not following the same format. However, the software tools that we are dealing with are expecting quite standard formats. And therefore, we had to somehow adapt our code to pick up automatically the expected types in PySpark, for example, from the server side. So that's exactly what we did. We are now extracting our data types from the server side. We are using some PySpark code to do that, and we are feeding it inside all our processing steps. It might not seem like much, but we were able to free up a lot of hours of debugging, because before all the matching between types was done manually, and therefore this is a huge improvement. The time of the presentation is almost over, and so is the presentation. So I want to quickly summarize what we've been discussing today. I really want you to keep in mind that fraud is extremely immoral, and it can affect all of us. But in the meantime, what we are doing is to prevent this fraudulent transaction from happening, and we are doing this either by scaling up models that are already present in certain countries to other countries where we are present, or by building new models whenever we see the opportunity. We are trying to keep our development fast. We are trying to not have any delays in our deployment, and regarding the old models, we are constantly trying to improve and upgrade them so they can stay in line with the behavior of the fraudsters. Now, if you have any questions, feel free to ask them.
Thank you so much. Thank you. Let's see if we can get some questions for Ștefan. Anyone interested in their money's safety? Yes.
There's been lately in Romania this frauds where they call you and they say you've been doing a credit on your name at another bank for ING, but at another sucursală. I don't know that. Yeah.
Brent? Yeah.
And then they're asking for your account credentials in order to get some money from there. Have you been able to filter any frauds from those, or do you know any cases that you've been able to mitigate this?
I know a case where I was involved in such a schema. My name was used for such interaction, and I, at some point, was contacted by our colleagues in a branch asking me, hey, did this really happen? And of course, it was a no answer. I cannot really tell you this. I'm not sure, and I don't want to give you any wrong directions. But we are usually not training our models to be specific for some ways of working of the fraudsters, but we are covering a large spectrum. So there is a high chance that some cases were indeed prevented. Probably not all of them, but probably some of them.
Thank you. Anyone else? Yes.
Hello.
Oh.
Is there a statistics, let's say out of 1 million transactions, how many do you detect with your engine?
Well, the imbalance when we are talking about fraud is extremely big. So sometimes there are cases where we have only one fraudulent transaction in 50,000 transactions. As I mentioned before, we have quite a large prevention system. I cannot really tell you how many of them are registered by the model, but in general, most of them are covered by the prevention system. So there are only few cases where clients are calling and are saying, hey, my money are gone. But this doesn't mean that there are not more cases of fraud that are happening, just that, as I mentioned in the beginning, people are not reporting it. And therefore, we cannot fully understand what is happening because people are not actually labeling their fraudulent transactions by themselves, so by calling the bank and telling details. But as we are aware now, most of the transactions that we use and we see as fraud are highlighted by the prevention system.
Thank you. Another question here.
Thank you. So at some point in the presentation, you mentioned an optimization that allowed you to process over 1 billion transactions in hours instead of days. I'm curious, was the source of the performance improvement down to a shift in architecture, in tool set, in data partitioning, parallelization, or a combination of all of these?
Thank you. Indeed, it was a combination of certain factors. It was not about the tools that we were using. It was more about how did we approach the problem. We shifted completely this way of attacking the problem. It was also about partition. We changed the way we partition our data to something more formal, and therefore we were able to have some speed ups also from this area. And yeah, I think these were the main components. We shifted completely the way we are dealing with the problem. And we got, of course, rid of any UDFs, user-defined functions, that we were including in our code because they were quite slow in comparison with some native functions that were available in PySpark.
Thank you. Anyone else? Okay. I have a quick question.
Sure.
Last 6 digits from your personal number. Thank you so much. Big round of applause for Ștefan, everyone. Thank you.